Thank you. Thank you, organizers, and thanks, Nirmal, for giving the slot. Otherwise, no, I would have gone without giving a talk. Right. So just made the title a little broader. Uh, so I'll just start with, I mean, it has two parts. In the first part, I'll talk about BIC and how the vectorial nature leads to OAM state upon reflection. And then I'll talk about how the plasmonic structures or the metamaterials can be used for light matter interaction, right? So this is something which we've been stuck with the editors for 3 years now. So the second part, which you will see, and uh, yeah, if anybody has an idea to improve, please let us know. Right. Just to start, because the title is light matter interaction, let's start with how light interacts with matter or matter responds to light. So we know that in bulk materials, the Lorentz model for dielectrics and Drude model for metals are used to estimate or to come up with these the bulk material parameter epsilon, right? So you have the standard simple harmonic oscillator with driven oscillator, in which in case of dielectric, because of the restoration force, like you have this, and that is absent for metals because electrons are free in metals. So this is for the bulk picture. And if you come to two-level systems and single photons or at the photon level, like so we talk about the Rabi model. The uncoupled Hamiltonian, if you look at it, it's a photon and then falling on a two-level system. How does that interaction happen? So that the interaction term is added by this third term here, right? But generally, over the last 60 years after the invention of laser, so what we have seen is mostly the rotating wave approximation, where we ignore these A dagger sigma plus and A sigma minus terms, and then you have this so-called Jaynes-Cummings Hamiltonian. We solve this and to explain most of the physics which we study so far, right? So the coupling terms, like so you can write them, so these off-diagonal terms are the coupling terms, and people have put the different regimes as weak coupling and strong coupling. The weak coupling, we know the examples of Fano line shapes or electromagnetically induced transparency, the Purcell enhancement. And in the strong coupling, people have demonstrated this Rabi splitting. The coupling constant here is stronger than the gamma 1, gamma 2, which are the damping coefficients for the cavity and the lifetime of the photon, right? However, over the last 10 years or so, this non-perturbative regime, so this so-called Jaynes-Cummings Hamiltonian is in the perturbative regime, where we are doing this approximation of a rotating wave and removing the fast oscillating terms. So, but here we are going into the non-perturbative regimes, which are the ultra-strong and deep strong coupling regimes. Here the G by omega, so here with the coupling constant, we no longer talk in terms of the damping coefficients, but we are directly comparable to the frequency of the resonance, right? So the G by omega, if it is of the order of 0.1, it's termed as ultra strong coupling regime, and if the G by omega is of the order of 1, it's a deep strong coupling, right? So just to illustrate this, like so the weak and strong coupling regimes, they are achieved with simple Fabry-Perot cavities with an atom inside that or a dipole emitter inside that, right? However, if you want to go to these ultra strong or deep strong coupling regimes, so you need to have a cavity, but instead of having very high quality factor, so that the lifetime, that the tau is very, very long, right? The cavity photon lifetime is very long, so that the interaction, the cross section of interaction increases. So instead of having very high finish cavities, now people look at this having a large density of these dipole emitters or atoms inside this. So the coupling constant now will not be just G, but it will be G times the square root of n, where n is the number of dipoles which are inside the cavity, right? So this is these regimes are interesting because now they show that actually the ground state itself gets modified now in these non-perturbative coupling regimes. So the physics as well as applications are being thought of as of now, right? So just to show the complexity, so there are only a handful of systems. They are mostly either the superconducting qubits or exciton polaritons, in which the ultra-strong coupling has been demonstrated. Deep strong coupling, there are only 2 demonstrations so far. Right. Again, these are in superconducting qubits at very, very low temperatures of millikelvins and things like that. Right. So it would be interesting if we could see at atmospheric conditions. Right. So what do we need to do? What do we need to study these light matter interactions? So first thing is you need dipole emitters or 2-level systems. Solid state equivalent of 2-level systems are quantum dots. You can take about defects in point defects in solid state materials, and now 2D materials are also coming up quite well. Other method which is least studied is metamaterials, which can mimic 2-level systems. Right. So we have one paper where we showed it. Actually, a couple of papers where we showed EIT as well as what is it like? Okay, I'll remember. I'll tell you. Right. Okay. So basically, idea is that you can design these metamaterials so that like you can mimic these 2-level systems inside these structures. EIT is of course the most obvious one, and here, for example, by distorting the shape of the metamaterial unit cell, so you can actually move from change the splittings, what you see in atomic systems, like so the orthogonal polarization states can be achieved just by in the scattered light components, right? So in addition to the 2-level system, so what you need is cavities. So there are different cavities. Sorry? This is no stretching. So when we are stretching it, the shape is changing. So these are on a PDMS stamp. So it's a stretchable metamaterial. So as you stretch, right, 20% stretching, you see that there is a deformation which leads to scattering in orthogonal polarization modes. No, after making them, so we apply force to distort these structures.
Forces are applied how?
By just micrometers in this case, right?
So there are like many micrometers are connected to each array, or
No, just one single thing. So we made sure that it's as uniform as possible. Right. So in the cavities, like people looked at starting from Fabry-Perot to whispering gallery modes, these are distributed Bragg reflectors. Then photonic crystal cavities, these are plasmonic cavities, as well as right now people are looking at this bound state in continuum. I'll show some of these examples in the next few slides. Right. I started off with bulk material properties, epsilon and mu. Right. So depending on epsilon and mu, whether they're positive or negative, we can have different conditions. For example, we can have in the second quadrant, mu is positive, but the epsilon is negative. So metals and plasmas are under this. And most of the naturally existing materials are the dielectrics. This is epsilon and mu, both are positive. The fourth quadrant is some negative mu materials like ferrites. And the interesting one is in the third quadrant with both epsilon and mu negative. So these are the negative index materials. As I'm kind of blanked out, like Nirmalya. As Nirmalya said in his talk, like, so the initially metamaterials are negative index materials, but now people talk about metamaterials in a general term where these are artificially designed structures with unit cell dimensions which are much smaller than the incident light wavelength. Right. So when in natural materials, when we talk about chemical composition and band structure, in metamaterials, the shape, size, geometry, and arrangement of unit cells defines the electromagnetic response of these materials. Right? So of late, people are using them for quantum information processing. So one of the ideas is to generate multiple beams and use them for trapping atom traps and ion traps. And this is one of the applications which people are looking at. So I'll show one example of single photon emission, directional single photon emission. And this one I will not be talking about, but basically people have reported, we also have seen this conductivity in organic semiconductors can be modified because of the plasmon coupling in these materials. Right. We have been working on metamaterials for more than a decade. So we looked at physics, for example, how we can modulate the material properties or what novel properties can be achieved using these plasmon coupling with the plasmonic modes, coupling with the magnetic resonances and things like that. So we looked at strong in-plane coupling of plasmons, the strong coupling regime, for example. Then with Subhasish, like, so this is all optical reflectionless potential. This is one of the all dielectric metamaterials. I'll show some on the plasmonic quasi-crystal, which Professor Jaldev also showed. So in the applications, we looked at on-chip Yagi-Uda antenna, for example, and switchable metamaterials for stealth applications. Right? I'll show some of these examples as I go along. Currently, we are looking at reusable biosensor and label-free biosensing with towards single molecule detection. Right. So in the there is a spin in the topic, like just to show like how the spin of the quantum dot. So for example, if you have a two-level system, a quantum dot, so the electron is excited to the excited state, and then it recombines with the hole in the ground state, and then it emits a photon. Now the polarization of the emitted photon is related to the electron spin inside the quantum dot. Right? If your electron spin is the qubit, which has the information inside the solid state system, then by measuring the polarization of the emitted photon, we can recalculate what was the spin state of the electron. Right? That was the idea which we proposed with photonic crystals. The idea here is to put a single quantum dot in this, and for example, in this, like, so there is a quantum dot here, you shine excitation source here, and then you measure the output. So for example, this is X and Z, like, so you can measure EX component here and EZ component here, and you can reconstruct the complete polarization state of the photon which is emitted. So that's what we demonstrated in a simpler structure. These are linear waveguides with a single quantum dot at the center. So by measuring the output at these two waveguides, so we could reconstruct and show what the electron state was. Right. So we are recently, like, we worked on the single photon emitters. This is based on the so-called hyperbolic metamaterials. So this is a 5-layer structure made of TiO2 and silver. And the quantum dot, a single quantum dot is placed inside the central region, center of the layer structure. And there is a patch antenna which is designed to be resonant with the quantum dot emission. The idea here is to get directional emission. So we can design the structure to come at any angle which we want, and how much collection efficiency we need can also be pre-designed depending on the objective which we use. So we showed selective excitation of quantum dot under the antenna, 200 times enhancement of emission, as well as 40% collection efficiency of photons coming out of this. Right? So one of the challenges is, which we have seen in the earlier talk, is about, he briefly mentioned about bleaching. Right? When you have these quantum dots, even any dipole emitter, even if you take about nitrogen vacancies in nanodiamonds, if you put strong light, even 1 milliwatt CW excitation is strong excitation for these nanoparticles. You see that if you are continuously illuminating, after a few seconds, the quantum dot or the nanoparticle just stops emitting anything. Right? It's just known as a photobleaching. In addition, there is another problem which these dipole emitters generally face, is the blinking. Right? So this, because it's a nanoparticle, the surface is always a defect, so because of which the electron can go, and the excited electron can go and sit in one of the defect states, and it doesn't recombine for very, very long time. It can be up to seconds, it can be hours, sometimes it can be months. Right? So this is known as the blinking. So what we have seen is, we studied it, we studied it, a large number of materials which will help in reducing this photobleaching effect, so that the quantum dots or nanoparticles are much more stable.
May I ask about it?
Yes, please.
Can you make this thing zero off measurement?
This one. Right. I mean, in ideal case, it goes to zero. We went down to, right?
Why don't you get it at 0 in your actual setup?
Right. There's always some background photon which may be coming in, so that's kind of noise level which leads it. But we have gone to less than 0.1, right? 0.05 kind of thing also, right? It's not one of the best examples, but yes, I mean, so it. So after all these material studies, what we found is hafnium dioxide, which is ALD grown. So that protects the quantum dots better. Even for the nanodiamonds, this is a good encapsulation. So the blinking, which I mentioned, like has reduced. Only the shorter intervals, like which we see, but otherwise you do see emission. And also the emission is stable over hours. And this is the Aharonov-Bohm dip to show that we have a single photon emitted from these structures. Right. So this work was with Shubhrangshu, where we showed that if you have two nanoparticles and embedded in a dielectric layer, which is brought close to a metal film, for example, so then this emission from one of the quantum dots can excite a plasmon mode, which can couple to the second quantum dot. Right. So these are two quantum dots which are basically coupled by the plasmon mode, and because of this coupling, we showed that the emission is basically is into noon state. So if you put two detectors, so both the photons which are emitted by the quantum dots, which are coupled by the plasmons, they come either in the D1 or the detector 2 direction. So this is the noon state possibility which we showed.
How do you excite the first dot?
So we can use, I mean, this is theoretical work, but we can use an ensemble tip, or we can use far field as well. Right?
Otherwise, how big are these dots?
These dots are few nanometers, if you want. But in this case, it's not needed to be, I mean, only one dot need be excited. We can excite both of them, but then because of the plasmon mode, there will always be coupled emission. Right. Right. So we studied different distances, but up to micron, they can be coupled. I'll show some example of the plasmon propagation length, which, I mean, that you can go up to few microns. 17 micron is the largest which we have seen. Right? So the bound state in continuum, so this is basically, we all know from the basic quantum mechanics problem, it's a potential well problem. If you have a potential well, you have these discretized energy levels within the potential well, but above the barrier, you see this continuum of energy levels. However, if there is a distortion in the barrier, for example, it's not smooth, but there is a roughness in it. So, for example, these are MBE grown, molecular beam epitaxy grown layered structures in which the composition fluctuation can be there, or the thickness fluctuation can be there in the layer. That leads to some roughness in the barriers. Right? So when you have a roughness in the barriers, it is possible to have a bound state within this continuum of energy levels. Right? This was proposed by Wigner way back in 1940s, but in 1980s, with the development in semiconductor growth, like so MBE grown samples have been used to demonstrate this bound state in continuum. Again, over the last few years, this has become very interesting for the nanophotonics community, because if you have scattering particle, for example, if you have a symmetric particle, so when you're coming at normal instance or gamma equal to or the gamma point excitation, so then you can have your dipole and higher order multipoles. They all emit in the same direction, so that the net emission is coming, or the net scattered component is along the preferred direction. Right? So this happens, the symmetry protected BIC, this happens in symmetrical structures where the emission can be, or scattering component can be along one particular direction. In I mean, if you can suppress them, it satisfies automatically. If there is only dipole, then it just satisfies. But here, it's just that, like, even higher order multipoles can also add up to give in the same direction, right? So that becomes apparent if you talk about the accidental BIC. Here, we don't need a symmetric particle. It can be any random shaped particle. Here, the vector sum of all these dipole and multipoles, they all come, and then the sum of it comes in one particular direction, right? So the accidental BIC can be used at off gamma point or non-normal incidence, right? And these are interesting because you have BIC mode is ideally an infinite quality factor mode. It's a mathematical abstraction because we cannot measure the zero line width or infinite Q mode. It can lead to directional emission and it has vectorial nature of the resonance. I'll show what it is, right? So we first studied one of the symmetry protected BIC. This is a structure having titanium dioxide disks, a square array on glass. So we calculated the band structure first and saw that like basically we have at gamma point the BIC mode with zero line width. And if you go slightly away from the gamma point or change the incident angle, you go to these quasi-BIC modes with finite, non-infinite Q factors. So that is seen here. So at zero angle, the BIC mode with zero line width is shown. But if you go to slightly off normal incident angles, you see that the line width is increasing. So these are the quasi-BIC modes with very high quality factors. But if you go even farther to larger angles, you see that the line width is increasing. Basically, these are the leaky modes which are coupling to the radiative modes in outside. Right? These resonances show asymmetry, like the Fano line shapes. Right? So interesting point is, again, these calculations were done with angular spectrum method, which Ian has described. So the interesting point from our study is that at resonance, at the BIC resonance or the quasi-BIC resonance, we see that the reflected spot, for example, remains spherical or circular in shape. But if you go to off normal, off resonance, we start seeing distortion in the shape, right? Shape of the spot which we are seeing, right? These are the near fields which were calculated. So we did measurements on one of the structures. So what you see is the circular symmetry. And as you go to off normal incidence, because this is a square lattice, you have 4 scattering elements here. So that's the distortion which you start seeing, right? And interesting point is this vector nature. So you have this L equal to -2 mode for this particular structure, right? So then we went on to show polarization independent BIC. So here the idea is that you start with a monoatomic lattice. All the disks have same dimensions, but if you modify half of these to have slightly different size or shape, so then what you're going is from monoatomic to a diatomic lattice. So because of which, what happens is that there's a zone folding. So this M prime point actually folds onto the gamma point. So now you have two resonances with two orthogonal polarizations which are coming onto the gamma point, because of which like your polarization dependence will go away. And for all polarizations, we showed it for linear and right, left, circularly polarized lights and all that, we do have polarization independent BIC resonance at this. So this is the experimental results for this, which showed that there is no polarization dependence for the BIC resonance in this case, right? So right now what we're trying to do is, can we control the high Q modes? As I showed, the idea is to get as high Q as possible, go as close to BIC mode as possible. So for that, instead of using dielectrics with non-magnetic materials, we are using magnetic material, for example, bismuth doped tritium iron garnet, which is a ferromagnetic material. So the disks are made of these ferromagnetic materials, and we designed these structures and simulated with and without magnetic fields and saw that like how close we can go, right? So these are experimental results. These are preliminary results which show that like actually we can go closer as we apply magnetic field, right? So this is the reflection data from these at resonance and off resonance, and the interference pattern showing the vortex nature of these reflected beams, right? So this is with magnetic fields, right? So I'll go to the second part now. which is, I'll talk about the plasmon exciton coupling towards ultra-strong coupling regime, right? So this is one structure which Nikolai has showed in the previous talk. It is a quasi-periodic pattern. So these are air holes in a thin gold film. So we showed quite a few uh, phenomena in this, including broadband linear transmission enhancement. So for example, we showed about 120, 140 times enhancement in the transmission over a broad wavelength range. There is strong local field which leads to harmonic generation. Hopefully I have something. No, I don't have. Sorry. We showed this second harmonic generation over the broad wavelength range. We studied the plasmon dynamics because it's a broadband response, so there is no structural dependence on the geometric dispersion does not contribute in this case. So we studied the pure plasmon dynamics in this broadband structure. It has very interesting near field properties as well as far field properties, which show these superoscillatory points as Nikolai has showed. So I'll show some of the our results here. So this is basically we deposit quantum dots on top of this. There is the structure is like this. There's quartz substrate, a metal film with air holes conforming to this 5-fold rotation symmetry. Then we put a thin layer of silicon dioxide spacer layer and then spin coat quantum dots on top of it, right? So this is a normalized transmission and reflection showing that this is a broadband structure. The interesting thing is, if you look at the quantum dot photoluminescence, the emission from the quantum dots, these are from the bare quantum dots, and this is on for example, on quartz substrate, right? So what you see is there is no change here, but as soon as these quantum dots are put on this structured surface, you see a blue shift of the emission. But compared to the gold, the patterned gold, there is a red shift, right? This red shift, we found it to be about 1.1 nanometer or so. So so this is something, a question why this is happening, we do not understand. So one argument which some people I talk to say is that it could be lamp shift, but we have not calculated it. We need to check this out. Right. This part, this is 20 nanometer. This is 10 nanometer. So this shift is I'm talking about. So this shift is quite large. This is about 10 nanometer, right? Right. Right. We don't know. It's the same density of dots, right? But right. This is on quartz, and we are comparing with the gold. So the gold always quenches a little, right? Right. So we measure both, but because it's a glass substrate underneath, we measure in both of them, right? But the one which I showed is reflection. Right? So we studied pump probe. The interesting part is it shows the decay as expected. So this is of the order of, like, say, there are three different, it's not very clear from here, but there are three exponential decays. I'll show a little later, much clearer data. What is interesting is if we go very close to zero delay, right? So this is the data which it shows, right? Okay. So here you see these oscillations, right? These oscillations actually go up to 30 picosecond. The plasmon lifetime is typically of the order. It's actually not of the order of, like, what we measured in these structures. The plasmon lifetime is 1 picosecond, right? And the exciton lifetime goes up to nanoseconds, right? These oscillations go up to 30 picosecond, much longer than the plasmon lifetime.
Individually, these look like one, right? Individually, if you see, they are like periods of
which?
Those individual oscillations, the gap is about 1 or 2 hours. Line width is also about 1, right?
One of what?
1 picosecond types, right?
No, they're not. They're much longer.
No, but your x-axis.
So the period, the frequency is 1.1. It's close to 1 terahertz. right? So that comes to 1 picosecond, right? Right. Right.
Here, the strong coupling is due to collective effect.
I'll show that,
Here
right?
10 to the power
Yes,
5 quantum
right. I'll show that. So these are we both, as I said, like we measure both reflection as well as transmission, so that there is no ambiguity. Like if maybe some absorption happening, something is happening. So we measure both reflection and transmission simultaneously, right? So we have detectors. Sorry.
Substantial absorption is there?
Is there, yes. So it's into the plasmon mode and then couples to the quantum dots as well, right? So the interesting thing is these oscillations are seen only on plasmonic quasi-crystal part, not on plain gold, and they're very weak in the reflection. They're seen more dominant in the transmission, and they do not appear when it is low density. Only for high densities we see the oscillations, right? Where the density is of the order of 10 power 5, so we see these oscillations. Yeah, as I showed, like, so this is the Fourier thing. So this actually, the period, it matches with the splitting. Okay, I'll just show one more thing, which is, this is the sample. This is the unpatterned gold, and then the quasi-periodic pattern is inside this region. Now we come with a beam, and then we measure the Gauss-Hanschen shift, right? So this Nirmalya mentioned in his talk, like, so basically we measure what is the shift in the beam position, right? So, right? This is longitudinal, right? So the idea here is that, so in case of plasmonic structure, if you have a metal and a dielectric, you have the interface, and then the plasmonic mode is possible, which is propagating along this direction, right? Now, if light is incident at this point, so there is always a shift in the beam position. The reflected, this is the incident, and this is the reflected beam. You can go up to 10%. You can go up to 10%.
10%. So that means you have substantial reflected light.
Right, yes.
The signal to noise ratio is not a problem.
It's not right. So the idea here is that, like, so unpatterned gold, the shift is about, like, I mean, the position of the beam is around this much, right? But on the plasmonic quasi-crystal compared to the unpatterned gold, we have a shift in the beam, which is basically the plasmon mode is excited. It's just propagating to certain distance and then getting recoupled to the radiative mode, right? So that's the plasmon propagation length, or the plasmon lifetime can be estimated from that, right? So in this case, this is about 17 micrometer in our case. So
You are looking at the centroid of the beam.
Centroid of the beam, yes, right.
An average centroid, right?
Right.
Intensity average.
Yes, right. 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 So what we use for this is that traveling, so we do not measure at one single position, but we move the quadrant photodiode across the beam, so that, like, we get about 50 nanometer resolution in our measurements. Right? So we do see these hotspots, and then this is the emission from these quantum dots. The emission is basically, the excitation spot is somewhere here, and 6 micron away from that. So we know the focal spot of the spot. So we leave about 6 micron from the edge of that spot, and then measure the emission coming from these quantum dots. We block with a notch filter, we suppress the excitation wavelength and collect only the emission. What we see is the quantum dots, which are up to about 17 micron or so from the excitation center. So they're all excited in this structure, right? So the model which we proposing is that, like, so this is the SEM image of the pattern. So we have quantum dots clusters on top of this, and this is, for example, a near field image which is in the background. So we see these topological pathways and all that. That's a different story. But here the idea is that the red ones are basically radiatively coupled, and these black ones are they're not excited basically, right? So now a quantum dot cluster which is excited here is going to re-emit, right? That emitted light from this quantum dot cluster is coupled to the plasmon mode, propagates along the one of the channel paths.
What is the distance between successive quantum dots?
So that's very narrow, very small, because this is 10 power 5 quantum dots per micrometer cube.
So do you consider the dB interaction here?
Right. In this case, we've not done any calculation yet. Like, so the dipole-dipole interaction will be there, and that is what is caused. We're saying that, but this is not short range, but this is long range dipole-dipole interaction mediated by the plasmons. Right. So that's what I'm trying to explain. Is that like, so you have dipoles here, you have dipoles here.
Those red patches are clumps of quantum dots.
Right, these are quantum dots which are radiatively coupled, which are excited, the electrons are excited, the excitons are formed, and then, right, so they are re-emitting. Right? That re-emission is basically coupling to the plasmons. These plasmons basically couple to a far away, though the excitation spot is only here, the plasmons which are excited by these quantum dot clusters, they couple to a cluster which is far away. Right? So we did, model, simplified model like this, the full, the complete quantum Rabi model to show these oscillations. They hardly decay because the exciton lifetime is nanosecond. Compared to that, like, so this decay is very weak, right? So we estimated G by omega. So from most of these things are calculated. So finally, the G by omega which we get is about 0.4 in this case.
So that was like a V system, no?
Sorry?
That's like a V system.
Yeah, right. So it's a ground state where no excitation is there. Like, so you have E2 and E3. So this is basically E2 can be on the pattern, right? And this E3 can be on the gold region, unpatterned gold region. So these two are getting coupled by the plasmon mode.
So do you see any kind of mode splitting and all here?
This is precisely the question which the editors have been asking, because in the strong coupling regime, the splitting is expected. In ultra strong and deep strong coupling regime, you have a shift in the position, and there is no theory to explain this yet, but splitting is not needed to talk about these regimes. Right.
For a request.
Right. I'm done.
Lecturer physics that
Sorry,
you-
I'm done.
You are already